This is a Math 2 lesson summary video for the task titled The Tortoise and the Hare. This is a solidify understanding task. The purpose of this lesson is for students to compare quadratic functions to exponential functions. In the children's story of the tortoise and the hare mocks the tortoise for being slow. The tortoise replies, "Slow and steady wins the race." The hare says, "We'll see about that," and challenges the tortoise to a race. The distance from the starting line of the hare is given by the function d equals t squared, where d is in meters and t is in seconds. Because the hare is so confident that he can beat the tortoise, he gives the tortoise a 1 meter head start. The distance from the starting line of the tortoise, including the head start, is given by the function d equals 2 to the t power, where d is still in meters and t is still in seconds. So what we're going to do here is compare the distance that the hare is running over time to the distance that the tortoise is running over time. And the distance that the hare runs is modeled with a quadratic function, and the distance that the tortoise is running is modeled with a exponential function. So if we look at these two models, here we have the tortoise and the hare, and I used Desmos to create a graph that represents both the tortoise and the hare. Here you can see the tortoise already has their 1 meter head start and starts out ahead of the hare, but as time passes, right here at 2 seconds, the tortoise and the hare are at the same distance, which if we look at our table, that would be 4 meters. So after 2 seconds, they both are 4 meters away from the starting line. And then the hare is going to be in the lead until the time is at 4 seconds, where they are both at 16 meters. And then after 4 seconds, the tortoise stays in the lead. In this task, you're asked to compare average rates of change. So let's find some of these average rates of change so we compare this quadratic model from the hare to this exponential model for the tortoise. So we're finding the average rate of change for each of these intervals. So these intervals are x values. And we're going to use the same slope formula that you learned when you learned about linear functions. So we'll start with the interval 0, 2. So I'm looking at the tortoise table where x is 0 and x is 2. So I'm using those ordered pairs, and I'm going to substitute these values into the slope formula. So I subtract my y's in the numerator, it's 4 minus 1, and my x values in the denominator, so that is 2 minus 0, and I have an average rate of change of 3 over 2. Now let's do the same thing for the hare. So I'm looking where x equals 0 and x equals 2. I'll subtract the y's in the numerator, 4 minus 0, and the x values in the denominator, 2 minus 0, and I get 4 over 2, or just 2. So here the hare has the larger rate of change. Now that should make sense from the graph, because if I look at where x equals 0 and x equals 2 for the hare, and I draw a straight line that goes through those points, now I want to compare this line to a line that I get when I connect these 2 points that are on the graph that's modeling the tortoise's distance from the starting line. So I can see here that this line that connects the points that are on my quadratic graph, the hare's graph, is steeper than the line that connects the points that are on the tortoise's graph. That's because the tortoise is only gaining 3 meters in 2 seconds, but the hare is gaining 4 meters in 2 seconds. So in this interval from 0 seconds to 2 seconds, the hare has a larger average rate of change. So let's look at the next interval from 2 seconds to 4 seconds. For the tortoise, we're looking at these 2 points. So when I use this slope formula and I'm finding the average rate of change in that interval, subtract my y's in my numerator and the x values in the denominator, and I'll find that this tortoise is traveling 12 meters in 2 seconds, so that would be 6 meters in 1 second. And then for the hare, I'm going to do the same thing. I'm going to subtract these y values in the numerator and the x values in the denominator, And I'm actually subtracting the same numbers because at 2 seconds and at 4 seconds, the tortoise and the hare were at the same distance from the starting line. So again, in this interval, the hare is traveling 6 meters in 1 second. So they have the same average rate of change. So finally, let's look at this last interval from 4 on to positive infinity. For the tortoise, as time continues to increase, the distance increases by continually multiplying by 2, because with this exponential function, common ratio is 2. The hare is modeled with a quadratic function, so it is changing by adding a linear value. So plus 9 and then plus 11. So repeatedly multiplying by 2 is going to make the tortoise's distance grow faster than the hare's distance, which is going to continue to increase at this linear pattern by adding increasingly large numbers that follow the linear pattern. This is also shown in the graph where we look at this curve for the exponential function for the tortoise. It starts to get steeper and steeper, and that's because it is growing exponentially. Exponential functions will grow at a faster rate. So let's summarize this. Quadratic functions grow at a linear rate. So that means that a quadratic function that has a minimum, like our example, will grow by adding increasingly larger values that follow a linear pattern. Exponential functions grow at an exponential rate. This means that an increasing exponential function grows by multiplying by a constant ratio that's greater than 1. Eventually, increasing exponential functions will always exceed our quadratic functions. So as long as the tortoise is willing to run a long distance race, she will win every time. All right, that's it for this video. Thank you for watching.